Let us see about the fascinating nonlinear waves called solitons. The soliton concept is an interesting concept that arises in diverse areas of physics, ranging from water waves, matter waves in bosons and condensates, to nonlinear optical waves. These solitons were first observed by John Scott Russell, a Scottish naval architect. In the year 1834, John Scott Russell, riding on a horseback, observed the great wave of translation in the Union Canal connecting the Scottish cities of Edinburgh and Glasgow. His original report appeared in Report on Waves in the year 1844 about this great wave of translation is shown here. The main content of this, Russell has drawn a boat along the canal by a pair of horses. When the boat was stopped, below the prow of the vessel, a huge solitary elevation was formed. Its height is around 1 to 1.5 foot and its length is of 30 feet. This long solitary wave elevation travelled through a long distance without change in its shape and without decreasing its velocity. And he called this wave as Great Wave of Translation. Following this, then Russell repeated several experiments in laboratory. He observed that the solitary waves have hyperbolic secant shape and they cross each other without change of any kind. This clipping shows the production of soliton in a laboratory. Here, a proper initial disturbance is applied and a soliton is formed that propagates without change in its amplitude and speed. This non-dispersive propagation is a significant feature of soliton. Then the ultimate explanation of the Scott-Russell phenomena was provided by the famous Dutch physicist David Korteweg and his student Gustav in the year 1895. They have derived the following nonlinear partial differential equation for the Russell waves. And they also found that this wave system supports a solitary wave solution. These solutions arose as a result of a delicate balance between nonlinearity and the dispersion. Their work and Russell's observations fell into obscurity and were ignored by researchers until 1965, when Norman Jablonski and Martin Trescal has published their numerical solutions of the KdV equation, which ultimately led to the notion of soliton. They show that the initial solution develops a train of 8 well-defined solitary waves with different amplitudes, each like a secant hyperbolic function. Here the taller wave travels faster and the shorter wave travels with less speed. These nonlinear waves interact strongly and then continue thereafter almost as if there had been no interaction at all. For a better understanding, here we have shown the interaction of two solitons. Initially, the two solitons are well separated, where the taller one travels faster and the smaller one travels with less velocity. So the taller one overtakes it, and after time passes, it comes out. After this collision, the two solitons appear intact. The only effect is the phase shift. That is, the center of each wave is at a different position than where it would have been if each one of them were traveling alone. This behavior is similar to the behavior of particle collision. So this led to the Jablonski and Trescal to coin the name solitons in analogy with photons, protons, electrons, etc. They call these solitary waves as solitons. So now we have seen about solitons. Now we are in a position to define solitons. Solitons are solitary waves that asymptotically preserve their identities like amplitude and speed during collision, except for a phase shift. These solitons, from a mathematical point of view, appear as a solution of certain nonlinear integrable partial differential equations. Nowadays, these solitons find application in several areas of physics as well as in science. Thank you.